Hello, my name is Marina Konkol. Through clustering, we were able to identify over 8,000 moving groups within Gaia data, with the ages of these moving groups ranging from a few million years to several billion years. This sample allows a deeper look into the star-forming history of the galaxy. We find that most young stars tend to form inside long strings that resemble the morphology of molecular clouds from which they are born. Eventually, these strings relax into the galaxy, leaving only densest and most cluster-like parts behind. We also find that young strings tend to be perpendicular to the spiral arms, suggesting a dominant process behind giant molecular cloud assembly. Spiral arms themselves don't remain stationary. They twist and turn, dissolve and reform over time, resulting in a very different spatial distribution of the moving groups found at older ages, in comparison to those that are still young. Please check out the poster to explore the interactive figures. Also, please visit the poster by Aidan McBride for a closer look at the more recent star-forming history of the solar neighborhood.
The Next Generation Transit Survey is a state-of-the-art wide-field photometric facility based at ESO's Paranal Observatory. NGTS is conducting a systematic survey of nearby young open clusters with ages between 1 megayear to 3 gigayear, which are each being monitored at 12-second cadence every clear night for up to 250 days. 10 open clusters have been observed to date, with more planned for the coming years. In Blanco 1, we find that the majority of mid-F to early K stars display evolving rotation patterns, whereas most M stars show more stable modulation signals over 200 days. In the Orion complex, we observed some of the most energetic white light flares to date, and estimate that early M stars in the complex produce very high energy flares at almost 1,000 times the rate measured for older M dwarfs. We've also detected new eclipsing binaries, flux dippers, accretion bursters, and complex rotators. If you'd like to know more, please get in touch with us and check out our posters. Thank you.
Hello everyone, my name is Cora Mujic from the University of Lisbon in Portugal, and we study properties of brown dwarfs in a wide variety of Milky Way environments, from the low density nearby star-forming regions to massive dense clusters rich in OB stars. And we compare their initial mass functions and number ratios of stars to brown dwarfs, and so far we see no evidence for any substantial differences between these different environments. And so if you want to learn more about the Milky Way substellar population, please, I invite you to check my poster, but also the posters by Carolina Kubiak and Victor Almendro Sabat, if you want to learn more about the membership determination methods and other more detailed results in the brown dwarf regime. Thank you very much.
Hello to everyone, I'm Maria Chiara, and during my PhD I want to characterize atmosphere of exoplanets and stars through the high spectral resolution. What I do is coupling the dynamics of the star and the planet in order to create a unique spectrum with both the contributions and in order to interpret the real observations. This is possible for two main reasons. Stars and planets share the same elements, like the CO lines that I'm showing you in this plot, but also they have the dynamical time scale very similar, especially for granulation and planetary winds. These two phenomena affect in the same way the profile line of the planet or the star's spectrum, because when the gas is moving and because the presence of velocities field, the profile line is deformed and also Doppler shifted. My goal is to model as precise as never before the stellar and planetary dynamics in order to study planetary winds, abundances, and of course better characterize both the objects.
Hi everyone, I am Joe Nainan presenting here how we probe the exosphere of planets around M dwarfs. Evaporating atmosphere has been a leading hypothesis to explain the dearth of planets at around 1.7 Earth radii. Recently, the helium-10-830 resonance scattering line from the metastable helium atoms have emerged as a powerful probe to detect these evaporating atmospheres. As explained in the poster, we started by modeling the outflows of M-dwarf planets and then observed with the Habitable Zone Planet Finder to detect these evaporating atmospheres. The first detection of helium-10-830 from a warm Neptune around an M-dwarf star was made in integer 3470. Our detection was 10 times fainter than what our model had predicted. This could be resolved probably by the uncertainties in the extreme UV radiation or a depletion of helium in the atmosphere of exosphere of these planets. For more details, please see the poster.
This is the main point of my poster. On the y-axis, I have stellar rotation rates as determined from photometric modulation from space-based observatories, mostly K2. The x-axis has V minus K color as a proxy for mass. I've got a whole series of clusters ordered by age here, from row F at 1 million years to Price-B at almost 800 million years. The gray points are another later cluster in the sequence to make it easier to compare by eye between clusters. The new cluster here is UCL LCC, which is test data. The structure that is so obvious by the Pleiades is starting to show up by upper SCO, and it seems to be there for UCL and LCC as well. The additional red circle means there's an infrared excess, in other words, a circumstellar disk. For the younger clusters, that's a primordial disk. For the Pleiades, those are debris disks. The pileup of the disk to M stars at about 2 days that we found in upper SCO is definitely still there for UCL LCC.
Hello. The project we have been working on is concerned with the activity and evolution of exoplanet-hosting stars. The hypothesis we were exploring is that close-in, more massive exoplanets may influence the rotation evolution of the host, making the stellar host more active than expected for given age and spectral type. To avoid the dependence on age in estimating the expected activity level, we only investigated planet-hosting stars that have a stellar companion, which we used as a reference for the expected activity level. As the activity indicator, we use the X-ray luminosity, which accounts for the activity of stellar corona. Although the sample does not allow for a definite conclusion, our results point us to a positive correlation between the activity level of the planet host and the strength of the star-planet interaction. Thank you.
Hi, my name is Luan Guesi, and I'm a professor at Federal University of Rio de Janeiro in Brazil. And together with my collaborators listed here, we determined new and independent meta-lists for stars in the California Kepler survey. And we use these meta-lists to try and check if they are somehow connected to the architectures of planetary systems. As previously reported in the literature, we confirmed that stars with hot planets are indeed more metal-rich on average than stars with warm planets. But we also find out that this difference is larger for stars with multiple planets relative to stars with single planets. Moreover, we find that this difference is even larger for systems with multiple super-Earths, and a similar result is not observed for systems with multiple subNeptunes, suggesting a possible difference within the small planet regime. If you want to know more about these results, please come check our poster or feel free to contact me by email. Thanks for your attention.
Is stellar evolution universal? Does the environment in which stars reside influence their evolutionary path? A particularly sensitive way of probing these questions for cool main sequence stars is via their angular momentum content, because it changes significantly with stellar age and can be probed easily through stellar rotation periods. On our poster, we present new rotation period measurements for stars in the zero-age main sequence open cluster CS20half and show that its rotation period distribution is virtually identical to the Pleiades and 3 other coeval open clusters. Hence, the star formation process seems to be universal and not influenced by the cluster environment. But there is more, including a new group of young, slowly rotating M-dwarfs with rotation periods up to 25 days, and a comparison of the X-ray activity between CS20half and the Pleiades, which is also the same rather than different as thought before. Go check out my poster and convince yourself on the similarities of these open clusters.
Hi, my name's Josh Briegel. I'm a PhD student at the University of Cambridge. I'm here to talk to you about my poster and upcoming publication entitled Extracting Stellar Variability from 1 million NGTS light curves. We're using data from the Next Generation Transit Survey based in Paranal, Chile, to conduct a systematic variability study. We use a generalization of the autocorrelation function, which is applicable to our ground-based observation schedule. We look at how this variability is distributed in different stellar populations, and how this could be related to stellar properties, for example angular momentum in our rotational signals. We compare our dataset with previous studies from Kepler, K2, and Mirth, and we observe a distinctive bimodal structure in the rotation periods of cooler main sequence stars. So if any of this sounds interesting, then please come and take a look at my poster or get in touch. Thanks.